Okay, good morning, good afternoon. Thank you for attending this webinar on wireless machinery condition monitoring. Condition monitoring is a primary enabler of increasing safety, increasing machinery availability, and increasing the top line, while simultaneously reducing environmental events, downtime, and operating expenses. Wireless is a key element of economical condition monitoring for the right class of machinery. ISA 100 protocol and standard is a foundational facilitator of getting that wireless data to the right systems and, more importantly, to the right individuals. As owners and operators strive to meet and exceed increasingly challenging production targets, understanding the health of their production assets is increasingly critical to meeting and exceeding production targets. Let's talk a little bit about production imperatives, and equally importantly, let's define imperative briefly. It's an obligation or a command that is unconditionally and universally binding. So it's something you've got to meet. So one example of that is production targets. And what are some of the challenges to meeting production targets? The inability to predict downtime, spending too much time on planned outages, trying to identify causes of process inefficiencies. In one vernacular, that's known as debottlenecking, getting more stuff through. Too much information, just rounding in everything that's out there available today. Not enough resources to actually predict downtime. We don't have too many Ouija boards within these facilities, unfortunately. And, of course, interpreting the data and ensuring that planned maintenance that is in place is focused on fixing the right problem. Some operational imperatives are the dealing with a growing shortage of skilled and knowledgeable workers, lack of standardization and approaches in equipment management, and those certainly drive high life cycle costs. In the ideal world, a common asset management philosophy is a combination of off-site and on-site intelligence. Having early foresight to potential problems that are coming up, and equally important, insight to focus on what's really what is the real problem that's come about. So what this does is it enables risk management from a strategic perspective and provides the system tools to sort and prioritize data and actionable information. And also provides the continual evaluation of analysis of developing issues. Okay, so needing to meet or exceed production targets. What are some of the challenges there? Well, certainly uncertainty around the cause of an unplanned outage and how long it's going to take to fix it. On planned outages, there's always uncertainty around how much time it's going to take to actually execute the outage and get things back into service. What are some ways to mitigate those challenges? Having a single condition monitoring platform that has predictive analytics, enabling you to look around corners when appropriate and be able to do a deep dive on the specific problem during a planned outage so that you've planned properly. What this does is it enables you to know the exact health of your equipment to avoid surprises. And when you do perform a planned outage, you spend less time on the actual work. You've got better insight into exactly what needs to be repaired. So automating early detection of anomalies is a key tool that's needed here. Controlling costs, what are some of the challenges there? If you don't know what's coming, a maintenance issue, it's more expensive because you've got to scramble high-cost resources to resolve the problem. Kind of a common theme nowadays is the shortage of skilled and knowledgeable workers in the right areas. And another challenge is having correlation between all of this data that's coming in. You may have 2, 3, or more different platforms that are collecting this data, and they all look and feel different. They have a different user experience, so having a common tool to look at this is certainly critical. Some of the ways to mitigate this, just touched on it, is having the global expert services team that you can draw on when needed. Customer training, having an organization that can provide training for helping you interpret the information that's coming your way. We've already talked about predictive analytics and, of course, the single platform. What does this mean to you? It's removing the surprises in equipment maintenance. It extends your internal team so that they can become smarter, more focused, more efficient, and allows you to see the condition of all of your rotating equipment, all of your assets. So bottom line is being able to act on correlated asset condition data. Okay, last but not least, reducing environmental health and safety risks. Unplanned outages expose personnel to risk. It's just you're not planning for it, so mistakes happen. That represents risk. And also distractions. You can't afford to have your focus taken away from EHS from unplanned events, in other words, distractions. Same set of tools that we've already touched on are critical to enabling you to reduce those distractions and to eliminate the surprises. At the end of the day, reducing machinery uncertainty is a driver to this. Okay, what are some key components of an integrated plant-wide solution? Well, certainly on the continuous monitoring side, you have rack monitors and distributed monitors that are, in addition to providing the monitoring data, they also provide protection as appropriate to the more critical pieces of equipment. Then on the balance of plant side that don't justify the higher value rack and distributed monitors, we've got wireless systems, portable data collection systems, wired scanning systems, wired continuous monitoring systems, and then application-specific systems. So in the case of motors, for example, you may have a dedicated device that captures and analyzes data that's very economical to install and deliver results to your condition monitoring and diagnostics platform, as well as your overall DCS system. What are some of the applications for wireless systems? Difficult to access, that are tough to get into. Maybe they're mounted or located in explosive areas where you don't want to send people in, if at all possible. Maybe a retrofit solution, maybe in a retrofit situation where you will experience a high cost of installing wiring to bring that data back to the condition monitoring system. Remote locations and lower cost assets such as pumps, motors, fans, small gearboxes, and valves, for example. Where would we apply wireless and where wouldn't we apply wireless? In its current state today, wireless is not a good candidate for protection systems for several reasons. And in addition, it's not permitted under one of the API 670 notes where critical turbo machinery that requires automatic shutdown, wireless would not be a candidate for that. Where it is a candidate is where periodic data as part of an overall program has high value. So one of the approaches to condition monitoring is a concept called the P to F curve. And briefly, there are multiple points on this curve where you can actually detect a potential failure that may be happening to the point where the failure occurs and the piece of equipment is no longer able to perform its intended service. And there's enough data, enough studies that have been performed that you can get a good feel for what that period of time looks like from when you can actually detect it, when the trends are starting to indicate there's a problem, until the equipment needs to be addressed right now. Wireless is a great candidate where you don't need to have continuous monitoring, where that time period is long enough that you can monitor on a periodic basis. The approach for ranking equipment with how critical it is and what type of failure mitigation strategy is presented here, and it runs the full spectrum from run to failure at the bottom. There's some pieces of equipment that are so low cost You just run them until they break. When they're broken, you replace it with a spare, and there's no impact on production. It's the least expensive way to deal with those particular pieces of equipment. At the other end of the spectrum is reliability-centered maintenance on your extremely critical equipment, where if it goes down, it's extremely expensive to repair, as well as has a major impact on your production capability. So those classes of criticality have a strategy associated with them for condition monitoring. Some of the technologies that are involved with those would be lubrication monitoring, thermography, vibrations, always a foundational, and also taking a look at the process variables, what's going in, what's coming out of this piece of equipment, and seeing how those are related to actually how the equipment's running. For example, if you've got a pump going into cavitation, you can see that directly in the vibration levels, as well as differences in the pressure differential across the input and the output. And again, depending on the criticality and the process that the equipment is involved with, that will drive how often you need to capture data from that particular piece of equipment. And then also some of the actions that are required as you're looking at this data, whether it's actual protection for the critical machinery that can cause significant damage if it goes out of bounds, predictive capabilities, so you're looking at the data and kind of have the capability to look around the corner for pending failure, as an example. So bottom line, what's the real value that wireless monitoring brings to the condition monitoring field of play? Well, with condition monitoring in general and wireless specifically, you have access to bringing in data from more assets more economically. And what this does for you is reduces surprises. Fewer surprises mean reduced cost. With fewer surprises, your equipment availability goes up, so your production levels go up. Wireless is easily expandable because there's no hardwired infrastructure required. What this enables is temporary and long-term surveillance and diagnostics. So if you have a bad actor piece of equipment that's tough to get to, but you need to have information from it, wireless is a prime candidate for that. You can go out once, instrument it, get the system set up, and start capturing data as needed. The wireless system can be left in permanently or just on a temporary basis. Avoids having to send somebody out there periodically to capture that information. And it also improves your human and capital resource utilization. We'll touch on that a little later. Where does wireless fit in the scanning system spectrum? Typically, you have a wired scanning system when you need to capture data on a minute-by-minute or hour-by-hour point of view, somewhere in that range. Wireless is a good candidate when you can extend it a little further, maybe from once every couple hours to once every couple of days or so. And then if you don't need the data because of the characteristics in that particular installation for that equipment, a portable data collector is the most economical way to go out and get that data, just as a general guideline. Okay, so now you've made the jump into wireless. One of the considerations there is how long are these wireless devices going to perform without needing attention? Specifically, how long does the battery last in them? Depending on how rapidly the data is being collected from the wireless device, the battery life can be anywhere from 3 to 6, 3 to 8 years, something on that order. So other options where you want to capture data more frequently and you're willing to sacrifice some of the battery life, you can, as indicated in the bottom left corner, you can see a line-powered power supply. It just comes off the power mains, bounced to a DIN rail, and provides power, continuous power to the wireless device, and it will run quote-unquote forever, for a long time, without needing a battery replacement. Another innovative source of energy is a vibration energy harvester in the upper left corner. it mounts to the rotating piece of equipment and captures some of the energy in the vibrations that come about from normal equipment operation. Very small amounts, but enough to provide power to the wireless SIM, or to the wireless device, and keep it going for a long time. And then one that's recently come about that looks very promising is a thermal energy harvester. And in installations, which are probably the vast majority of them, where there's a temperature differential between the air and the equipment that's being monitored of 20 degrees C or more, that temperature or thermal energy harvester provides enough energy to keep the wireless device running for the foreseeable future. So lots of options, lots of inexpensive options that further improve the value of wireless data collection. Some of the data that is available today in the wireless sensor systems, a prime example of that would be on a roller element bearing, which is the vast majority of equipment that is used in the vast majority of equipment that this is a candidate for. And so some of the data there would be a waterfall spectrum of frequencies, and it allows you to see the full spectrum over a period of time, and visually quickly be able to see changes in the characteristics of that roller element bearing. Those frequency spectrums change as the condition of the roller element bearing changes. And a key analytic tool is acceleration enveloping. That enables you to significantly reduce those frequencies that are not of interest, and allows you to focus on those that are of interest, that are true indications of bearing health. One example of condition monitoring in a roller element bearing is presented here. As you can see with the waterfall spectrum in the upper left corner, over a period of roughly a month, about 30 days, the spectrum changed, the characteristics changed, and as we got to the end there, a failure, which was indicated by the red line, came about. And just you can see from the trend there that the bearing was getting ready to fail. And the spectral analysis pointed a specific failure within the bearing. And once they pulled the bearing off and did a review of it, the inspection showed that the diagnostics were spot on. Lots of examples of that. What are some target applications for wireless condition monitoring? Tank farms and fin-fed heat exchangers are prime candidates. Tank farms, because of the big distances to be covered between the tanks and the pumps that are associated with them and other equipment, makes it relatively expensive to send an individual out there on a regular basis and go from point to point to point to capture the data. Wireless is a prime candidate there. And certainly heat exchangers, where you've got fans that are located very high, the motors are at the top, and difficult to get to, are great examples of where wireless would be a good fit. Some examples for wireless that we can relate to cite are a tank farm where data was captured at 3-week intervals for the pumps and the motors driving those pumps. And the problem with that is the motors or the pumps could fail more rapidly than every 3 or 4 weeks. And the reason that's a problem is the failure mode happens more quickly than the rate at which you're capturing data. So undetected failures can occur between rounds. Conceivably, you could go out on day 1, capture the data, and maybe a day or 2 later, the pump would actually fail. Its failure mechanism can happen that quickly. So a great solution there is putting a wireless system in to capture points on the pump and the motor and capture the data several times a day, and quickly the trend there can become apparent. Once those trends start to go up, you can send a technician to go out and take a look at that and verify that there is in fact a problem. Heat exchangers, fin-fan heat exchangers are another candidate. The current practice was to walk around on a monthly basis, but in some cases the cooling elements would become fouled and no longer be able to perform, and that would happen on a much faster rate than once every month, again over a period of several days or weeks. So by putting a wireless condition monitoring system in place there, it can capture that information minute by minute or hourly or daily basis rapidly enough that you're measuring at the right point. So in terms of actually deploying one of these systems, one example was the balance of plant machinery on a steam turbine at a power plant, and the intent was to add this collection of machinery to the existing condition monitoring system, and also to enable remote access for monitoring and support, so someone else off-site could be monitoring this in addition to those individuals on-site. So for this installation, there were 21 points that were deployed in 2 days. The equipment they were installed on were the feed pumps, the condensate pumps, water circulation pumps, forced draft fan, the water pumps, and lube oil pumps. The results were validation of how easy and simple it was to deploy, how fast it was. Anomalies, some problems with some of the equipment were quickly identified. And one example was that the cooling water pump was getting ready to no longer serve. That was verified properly by going out with a portable data collector, doing some more analysis on it. And in this case, it was pretty critical because that pump needed to work in the summer months so that the plant could continue to deliver energy. So closing up here on some of the benefits of ISA 100 and why that was attractive to us. Being an open source meant it was easy for us to bring that into our system, fairly straightforward to get the technology wrapped around that. It's a mature standard. There's a strong commitment from the ISA 100 community to make sure that this is successful, and I think that's evidenced by the number of manufacturers that are continually being added. At the time, it was the only protocol that supported the large data sets that machinery condition monitoring requires to deliver the waveforms and the fast Fourier transform information to the consumers of that. It also plays nice with wireless HART, so that's a benefit for everyone. Bottom line was, it provides a lower installation cost. It's less expensive to operate and very low maintenance throughout its life cycle. Takeaway here for us, this plays nicely into the big data and smart machines concept that's coming about. Certainly Cisco and others have their terms for it, but at the end of the day, you've got, as we touched on earlier, large amounts of data that need to be analyzed quickly, inexpensively, and boiled down into really what the root cause of what's being observed or what the problem is. And ISA 100 is a great highway for delivering that information. It plays nice in congested wireless environments, as noted by the paper here at the bottom, and it supports a large number of devices. When this was written, it looked at 500, and certainly that's going to grow over time as capabilities continue. And of course, the Wireless Compliance Institute, key element there is the compliance testing to ensure the interoperability among all certified products. There's a lot of manufacturers out there. They all bring value to the table, and we all need to get that information to really paint the big picture. So again, having that standard platform, standard conduit is critical. So in summary, condition monitoring is a key enabler of increasing the safety, increasing machinery availability, and increasing the top line. and at the same time reducing environmental events and operating expenses. Wireless is a key element of an economical condition monitoring platform for the appropriate classes of machinery, and ISA 100 protocol and standard is a key facilitator of getting that data to the right systems and to the right individuals. Thank you very much.